What I would like to look at is residual management. I've provided the background information. It's just one lecture that's posted on the recorded lecture slides in the folder. And that provides you with a lot more information about the principles of residual management, sludge types, characteristics, management of sludge, and ultimate disposal. What I'll focus on today is just a little bit of an overview along with some of the computations. Really much of this we've actually already covered, and it's just a review. You do need to address residual management in the final, in Mini Design 3. So hopefully this will help with addressing those issues. As the saying goes, there is no free lunch. Almost every process and activity at the water treatment, wastewater treatment plant produces a waste stream of some sort. Some of those are air streams, some of those are liquid streams, some of them are solid. If it is recycled and where it is recycled really depends on the quantity, the quality, and the needed treatment. And we're seeing this particularly with PFAS. We haven't designed wastewater treatment plants to remove these more complex chemicals. They're not designed to remove microplastics. They're not designed to remove PFAS. They're not designed to remove many of the pharmaceuticals, actually any of the pharmaceuticals. If they remove pharmaceuticals, it's purely serendipitous. Happens to be that those pharmaceuticals are degradable in the wastewater treatment plant and then removed. You may see that backwash water is recycled. In other cases, it's not. If we're looking at filter backwash, we really have two options. We can recycle it to the headworks of the plant, so before any other treatment is done, or we can discharge it to the sewer. If we discharge it to the sewer, it becomes the wastewater treatment plant's problem, basically. Very rarely now can you discharge filter backwash water to the source water. It used to be that we could, but very, very rarely can we do that now. Typically, if your source water, for instance, has high algae, it's recommended that you don't recycle because of the concern for buildup of chemicals like the microcystins, the exotoxins that are released by the algae. So this is a figure from the textbook from chapter 16, which talks about residual management. Relatively simple process. They have an ozone contactor. The calcium thiosulfate is actually used to quench any residual ozone. They add alum. They use sodium hydroxide for pH control. They've got a mixer, so they've got rapid mixing, flocculation, sedimentation. They disinfect with sodium hypochlorite before the filters. They call it on here a stabilization basin. Really, this is a clear well. And then pumps. Now they have a secondary process. They expanded the plant, but rather than expanding the plant with the exact same process, they expand the plant with membranes. So they add alum as a coagulant. This is an unusual situation that I would see that because adding alum as a coagulant produces floc, which will be captured on the membranes, but will also increase the fouling will increase the pressure, shorten the service life of the membranes before they have to be cleaned. And then they have a pump. They add sodium hypochlorite, and then they mix the two. Okay. So this is the general process of the plant. This, on the other hand, is the process diagram for the residual management. And this isn't even complete. They show here the filter backwash. They treat the filter backwash by adding alum and polymer to thicken the sludge. They also have, and this is quite complicated, why they actually have both of these processes, I'm not sure. There isn't enough detail in the textbook to explain why they have multiple processes for both solids thickening and dissolved air flotation. The difference between this is they're both thickening processes, but one uses gravity, so your solids thickening uses gravity. Dissolved air flotation uses what we refer to as flotation. It's the opposite. You're adding dissolved air, causing those solids to float to the surface. And then you capture the material that's floating on the surface, and that has a higher solids content, lower water content. Okay? And ultimately, they have a sludge lagoon. Now, the membranes also have to be treated. Those have to be backwashed, so they have backwash water from the membranes. They also typically have to be cleaned in place. That's what the CIP stands for, and those typically use weak acids or weak bases to try and remove any scale that is formed on the membrane itself, and better remove this particulate matter. And then they use alum and polymer for the dissolved air flotation and combine their streams and ultimately treat with a sludge lagoon. So, and you can see here the liquids are recycled to the head of the membrane. So that would get recycled to this portion right here. Okay. Same thing, any recycle from, I'll call it plant 1, would get recycled before the ozone plant. So just kind of thinking through the processes that we have, or the types of residuals that we may have. So think about this with your treatment plan. And you should be thinking about this from the headworks of the plant all the way through. So when you're thinking about residual management, think about now the entire plant. Okay. So we can have spent filter backwash. You've got sludges from your clarifier sedimentation basins. If you have GAC, you have the spent GAC once the GAC is exhausted. Or if you're using powdered activated carbon, you have the spent PAC, which typically will be mixed in with your sedimentation sludge. If you have a sludge lagoon, you've got any overflow or supernatant from that sludge lagoon. Typically in a water treatment plant, you won't have sludge drying beds, but these can be used in wastewater treatment. So you'd have the under drain from the sludge drying beds. Again, this is wastewater. If you have any thickening, dewatering processes, then you've got the supernatant from that. So for instance, at the East Lansing plant, they have sludge lagoons. So they dewater the softening sludge from the lagoons. Any supernatant from that, so we've got so if you look at the aerial photos of the East Lansing Meridian Township Water Treatment Plant, you'll see the sludge lagoons. That supernatant used to go back to the headworks of the plant. That meant that while this plant is a groundwater plant, it becomes a groundwater under the direct influence of surface water, which means that all of the surface water rules now apply to that plant. That makes it actually more difficult. There's more sampling that needs to be done out in the distribution system. There's more sampling that needs to be done at the plant. So they actually have stopped doing that. There's really only one alternative, and that's to get permitted to send that to the sewage treatment plant. And that requires a pre-treatment permit to discharge. On the other hand, the Lansing Board of Water and Light dye plant uses plate and frame press. So that's how they dewater. They actually thicken with gravity thickener, and then they have a plate and frame press, filter press. Their supernatant goes where? Anybody want to suggest where would their supernatant, what do they do with their supernatant from both the gravity thickener and the plate and frame filter press? That goes back to the headworks of the plant. The difference is what? What do you think the difference is with the Lansing Board of Water and Light dye plant, where they use gravity thickening, so their filter backwash water, their sludge from the softening process, okay, goes into a gravity thickener, which basically it's a sedimentation basin is what it is. Then through plate and frame filter presses to dewater the sludge. So what's the difference between the Lansing dye water plant and the East Lansing Meridian Township water treatment plant? There is a difference that they're privately owned. Okay, so the Lansing Board of Water and Light dye plant is privately owned. One thing to recognize, they're both community water systems. In terms of regulations, it doesn't matter whether a treatment plant is publicly owned or privately owned in terms of the regulations. Okay, they're a community water system. So as a community water system, both plants have to comply with the exact same regulations. There's some differences in sizes of plants in terms of the regulations, but not in terms of public or privately owned. So it's actually, thanks for mentioning that, because it's important to recognize that. So what's the difference? In the building, outside the building. Exactly, interior versus exterior. That is the difference. Okay, the sludge lagoons are outside, which actually means that geese can swim in them. Birds can swim in them. They're fenced, but if the deer get in there, the deer can drink out of them, poop in them, whatever. Okay. The gravity thickener and the plate and frame filter press are both internal. They're in the building. That water never sees the light of day. So it has no chance to become contaminated. So it is truly a groundwater plant. East Lansing Meridian Township have made some process modifications in their plant so that they no longer recycle that supernatant from the sludge lagoons in order to become a groundwater plant again, and not to be a groundwater under the direct influence of surface water. So that's an important distinction. If you're designing a plant and it's a groundwater plant, if you can avoid it becoming groundwater under the direct influence of surface water, it's beneficial in terms of sampling regulations, regulatory compliance. Other liquids that we can have: ion exchange regenerant brine. This is a highly concentrated brine solution, and because you're regenerating on a cycling basis, it's essentially a batch process discharge, which also means that potentially, if this is going to the sewer, depending on the size of your plant, that can potentially overwhelm the sewage treatment plant. So you may need to have storage and then slowly, essentially bleed that brine into the sewage treatment plant so as not to have a spike of total dissolved solids into the plant. And that really depends on the size. May have waste regenerant from an activated alumina plant. Membrane filtration concentrates, clean in place liquids from the membrane system. May have gases, off gases from stripping. So for instance, if you have an aeration process, for instance, to oxidize iron 2 to iron 3, or to remove CO2, you have off gases there. You have ozone off gases. In a wastewater treatment plant, you have the off gases, also aerosols from your aeration basins. If your treatment plant is very close to the public, so residential areas, you may need to actually put a cover on the aeration basins and filter or treat that off gas before discharging it to the atmosphere. Did I forget anything? Can you think of any other residuals that I didn't mention? I think I've got most of them. But make sure you're looking, when you're writing this residual section, make sure you're thinking of your entire plant. So in terms of sludge management, a number of things you want to think about. One is minimizing sludge generation. You don't want to overdose chemicals. One, it's going to cost you, but it's also going to produce additional sludge. With softening, how did we minimize sludge generation? What were some of the ways we talked about with softening? Talked about stripping the CO2. So if our CO2 levels in our groundwater were too high, we aerate to remove that CO2. Why? Because if you go back, think about reaction 1. Reaction 1 removes no hardness, but it costs us chemicals and it costs us sludge production. We also talked about using split treatment. Again, thinking about what can we do to minimize sludge production. If you can recover precipitates and reuse them, there is research being done, for instance, to capture that calcium carbonate sludge that's produced from softening, treat that to produce lime, so basically to strip off that CO2, and then reuse this in the plant. Problem is it's extremely energy intensive to do that. And this has been the biggest problem with reusing that calcium carbonate sludge. Reducing the volume of the sludge. And this is important because it can reduce disposal costs. Disposing of the chemicals in an environmentally friendly manner. This has been a major problem with the PFAS chemicals. Okay. PFAS chemicals, as I mentioned, we don't degrade in the wastewater treatment plant. So where do the PFAS chemicals end up? Where's the most likely place for the PFAS? If you've got PFAS chemicals in your plant influent, where are they going to end up? Exactly, in the sludge. Okay, so they end up in the biosolids. Problem is, if we use those biosolids as a land amendment and we grow crops on those, where do the PFAS end up? In the food, exactly. Okay. That has been one of the major problems with PFAS chemicals, is essentially recycling these chemicals through the environment. And we've used PFAS in just about everything. The Lapeer plant took waste from an electroplating operation. The electroplating operation used PFAS chemicals. There was no permit in the industrial pre-treatment permit, or no information in the industrial pre-treatment permit for that electroplating operation that dealt with PFAS. So where did the PFAS go? To the wastewater treatment plant, to the biosolids. They were using the biosolids as a land amendment, and then they started seeing significant concentrations of PFAS in the soil and in the crops. And it became a major issue, not surprisingly. Okay. So we need to think about protecting public health and the environment. And as a reminder, I've provided you with the ASCE Code of Ethics. It's changed slightly. The essence hasn't really changed. Still, above all, protection of the health, safety, and welfare of the public is paramount. That has not changed. It's changed the way that they no longer talk about canons. They talk about stakeholder group responsibilities. But always remember, okay, protection of the health, safety, and the public and welfare of the public. That's another thing I'm asking you to address in your mini design 3. So when we talk about sludge treatment, we typically divide up this treatment into stages. So, and I've mentioned some of these. So thickening, we're looking at removing water. typically preparing the sludge for further treatment. So it's assisting with further treatment. So I mentioned in the Lansing Board of Water and Light plant, they thicken with gravity thickener, and then we'll add the next process. So this is typically gravity or flotation. So if the sludge is very light, so for instance, with an activated sludge, so the waste activated sludge, predominantly microorganisms, those microorganisms are less dense than water. They float really well. So that's typically where you'll see flotation used. Conditioning, we're looking at some sort of chemical or physical treatment to improve dewatering. So for instance, you may add polymers in order to improve dewatering. Okay. And then the lastly is dewatering, and I mentioned here, they use a plate and frame filter press. In the pre-recorded lecture, I have videos of, in fact, I actually have a video of the operation of the Lansing BWL dye plant's plate and frame filter press. So here you're looking at dewatering, removing water, and we can do this by non-mechanical. So a lagoon, sludge drying beds, or we can use mechanical. So for instance, the plate and frame filter press, belt filter press, centrifuge. So there's a number of mechanical processes that we can use to dewater the sludge. What isn't shown here is stabilization. Stabilization is most often done with wastewater treatment. We're looking at converting organics to CO2, phosphate, if we can, nitrogen, and sulfate. So we're trying to convert all of our compounds to compounds that won't, one, we don't want them to smell. We don't want them to have a significant oxygen demand. And these include aerobic digestion, anaerobic digestion, also wet oxidation, incineration, composting.
Let's look at an example problem where we need to calculate the amount of sludge produced during coagulation treatment.
Data. So you have a plant with a flow rate of 0.05 cubic meters per second. You're told that you're dosing with ferric sulfate, and you're told that the initial suspended solids is 36 milligrams per liter. The effluent suspended solids from sedimentation is 1 milligram per liter. So we've got a conventional treatment plan. We've got rapid mix, we've got flocculation, we've got sedimentation. Okay, and we've got this, the sludge from the sedimentation. You are told that the sludge solids content is 1.05%, and the specific gravity of the sludge solids is 2.5, and you're asked for the volume. Now, The problem actually states that the dry solids produced is 46.2 kilograms per day. I'm just going to quickly go through that calculation as a reminder of, you've done this calculation, you've got it from mini design 2. If you've made any changes in your process, make sure you take that into consideration. But we have Fe2 SO4 3 plus 3 waters produces 2 ferric hydroxide plus 3 sulfate plus 6 hydronium ions. And we're adding 20 milligrams per liter. The molecular weight of ferric sulfate is roughly 400 milligrams per millimole and 106.87 milligrams per millimole for ferric hydroxide. So we have 20 milligrams per liter divided by 399.91 milligrams per millimole. That gives us the millimoles of ferric sulfate. We will produce 2 millimoles of ferric hydroxide for every millimole of ferric sulfate that we add. And ferric sulfate has a molecular weight of 106 milligrams per millimole, and that is equal to 10.69 milligrams per liter of ferric hydroxide. To get the mass produced, we have 10.69 milligrams per liter times our flow rate times 1,000 liters per meter cubed. So let's say meters cubed cancel, liters cancel. We need 86,400 seconds per day. Sorry. And we have 10 to the 6 milligrams per kilogram. And that is equal to 46.2 kilograms per day. So that's where that 46.2 comes from. So we're looking at calculating the amount of sludge that's produced. We also need to take into account the suspended solids. So we have 36 minus 1. That's the rest. 1 is in the effluent. The rest ends up in our sludge. Again, 0.05 meters cubed per second, 1,000 liters per meter cubed, 86,400 seconds per day, and 10 to the 6 milligrams per kilogram. And that is equal to 151.2 kilograms per day. So our total solids is equal to 46.2 plus 151.2, or 197.4 kilograms per day. We've calculated that we have 197.4 kilograms per day. Our solids content is equal to 1.05. Okay. We were told this is our percent. Okay. And this is equal to the mass of the solids divided by the mass of the solids plus the mass of the water times 100. Okay. Or we can write it as 0.0105, and then we just have the mass of the solids divided by, because we just don't have the 100. And this is equal to 197.4 divided by 197.4 plus the mass of the water. I'm just going to write this as 0.0105. So I'm not using the percent. And if we solve this, the mass of the water is equal to 18,602 kilograms per day. The volume of my sludge is equal to the volume of the solids plus the volume of the water. I'm assuming that there's no interactions between the solids and the water that would change that volume. So basically it's not gelatinous. If it was gelatinous, it would change that volume. And this is equal to the mass of the solids divided by the density of the solids plus the mass of the water divided by the density of the water. And we said that the density of the solids was 2.5. Okay, so that is equal to 197.4 kilograms per day divided by, multiply the specific gravity times the density of water plus that 18602 kilograms per day divided by the density of water. And this is equal to 18.7 meters cubed per day. So notice most of this is water, which is one of the reason why we want to dewater this sludge. Okay, notice, so sludge coming from our sedimentation basin, okay, is only typically maybe a little bit more, maybe 2%, but it's relatively low in solids content, which is why we typically want to treat it further and remove as much of the water as we possibly can before we dispose of that sludge in whatever means we do. So when we're dealing with wastewater sludges, we often have to deal with the fact that we have both an inorganic or fixed fraction and a organic or volatile fraction. So when we're looking at determining the mass of the wastewater sludges, that mass is the sum of the component, the fixed fraction and the volatile fraction. And we then can determine the specific gravity of the solids using this equation here, which is really just a rearrangement of this previous equation. So let's look at an example where we are told that we have a primary settling sludge and flow rate of 0.1 meters cubed per second. We're given an influent suspended solids concentration, the removal efficiency of the suspended solids. We're told that our sludge solids concentration is 5% and that the sludge is made up of 60% volatile solids or organic fraction with a specific gravity of 0.99 and 40% fixed or inorganic solids with a specific gravity of 2.65. So let's work through this problem here. Again, let's just write out the information that we have. Q is equal to 0.150 meters cubed per day. The initial suspended solids concentration is 280 milligrams per liter. Our removal efficiency is 59%. The sludge solids concentration is 5%. The volatile solids fraction is 60%. Sub V is equal to 0.6. The specific gravity of the volatile fraction is 0.990. So it's designated as SB. The fixed solids comprise 40% of the solids. Therefore, P sub F is equal to 0.4. And the specific gravity of the fixed fraction, or S sub F, is equal to 2.65. The specific gravity of our solids is equal to M sub S, the mass of the solids, times S sub F times S sub V over the mass of the fixed fraction times S sub V plus the mass of the volatile fraction times S sub F. And M sub S is equal to M sub F, the fixed fraction, plus the volatile fraction. And that is equal to 0.4 plus 0.6, that's our fraction. And we're just going to let that equal to 1. It makes the problem a little simpler. And really what we're looking for is the suspended solids, sorry, the specific gravity of the solids. So S sub S is equal to 1 times 2.65 times 0.990 divided by 0.4 times 0.990 plus 0.6 times 2.65, and that is equal to 1.32. So that's the specific gravity of our solids. The specific gravity of the sludge is equal to S sub S over the fraction of solids plus the specific gravity of the solids times the fraction of water. And that is equal to 1.32 divided by 0.05, which 5% solids, plus 1.32 times the fraction of water. So if we have 5% solids, we have 95% water, and that is equal to 1.12. So that is the specific gravity of our sludge. So this is the sludge, and this is the specific gravity of the sludge solids. So first value, that 1.32 doesn't include the water. The mass of sludge is equal to the fraction removed times the influent suspended solids concentration times our flow rate times conversion from seconds to days. So seconds cancel, times 1,000 liters per meter cubed. So liters cancel, meters cubed cancel, times 10 to the 6 inverse milligrams per kilogram in milligrams cancel, and that is equal to 2.14 times 10 to the 3 kilograms per day. Now that's the dry solids. The volume of our sludge is equal to the mass of the solids divided by the density of water times the specific gravity of the sludge times the fraction of solids and that is equal to 2.14 times 10 to the 3 kilograms per day divided by density of water 1,000 kilograms per meter cubed times 1.012, the specific gravity of our sludge, times the fraction of solids, which is 0.05. Kilograms cancel, and we have meters cubed per day, and that is equal to 42.3 meters cubed per day. And that is the volume then that we would either have to treat subsequently or the volume that we would have to dispose of per day. So based on this lecture and chapters 16 and 27, you should be able to discuss the basic processes used for sludge treatment and explain their purpose and estimate volumes of sludge generated for both water treatment and wastewater treatment systems.